like that school will be like reversed to you holy crap, yeah, fully automated robots. I heavily advise so there's no human that we still take it seriously because I'm not going to put the test on it, but I'm still going to have homework on it. Okay, exponential functions. What are the differences between y equals x squared and y equals 2 to the x? For like brain surgery. So you can state some obvious things if you wish. It's y. There's a y in both, correct? Yes. Yeah, where's the variable? Here the variable is, do we know that word? Base, and here the variable is the exponent. This guy goes up way quicker. Way quicker. If the tumor's not there, right? Essentially what you're doing is you're doubling every time you go 2 to 4, 8, 16, 32, 64, 128, to 2, 50, whatever, 66, I don't know, 56. 256. Ultrasonics? Yeah. And then 512, 1024, 2048. 4,090. Yeah. Alright, that doubles a lot faster than 1 squared is 1, 4, 9. I'm doing the sort of 16, 25, 36. You see how this one's a lot faster going up as x goes up? That's the big idea. So we have mainly double functions that have a variable as the base, such as y equals x to the 5th. This is known as a power function. I wouldn't worry about that. Here's something we should be used to. Functions in the form y equals b to the x, where b is a positive real number, and the exponent is the variable. It's called exponential function. The reason we don't like it being negative is because if b was negative and we kept raising it to different powers, right, it would be positive on the even ones and negative on the odd ones, and we'd get a graph that's like kind of crazy, right, discontinuous, right, from this point to this point it would change. So, and then let's just think of like what y equals 2 to the x looks like. Here's our x, and here's our y. And I'm just thinking about y equals 2 to the x, just to get us an idea. What happens when x is 0? What is y? What is 2 to the 0 power? 1. Anything to the 0 power is 1. Hey, if we start plugging in values of x, like I was saying out loud, I said it gets big really fast, right? Like really fast. So as x goes out to a larger and larger number, we're raising 2 to a larger and larger power, and it just skyrockets, right? What happens on this side? What happens when x is negative? It gets smaller now. It goes down. So let's think about it. What is 2 to the negative 2?
1/4.
Yes, it's 1 over 2 squared. What's 2 to the negative 30?
1
over 2 to the 30, right? You will notice something. We can keep making the negative bigger. Right?
Oh!
And what does it never cross?
The x-axis.
0, right? Because we just keep getting a smaller and smaller fraction, and it just gets so close, but it never touches. That's what 2 to the x looks like. And if you did negative 2 to the x, not negative 2 to the x, but just a negative out front, you would just flip it. That's just to give us an idea. What do you think happens for y equals b to the x when b is greater than 1? So maybe it's just more than 1.
then I'll look at 2. We saw what happened with 2, right? If b was 2. Oh, we get like this kind of thing, right? What happens if b is in between 0 and 1? We said it can't be negative, but what happens if b is like 0.5? Start plugging in values in your head. When x is 0, what is y? Still 1. That's the same. If you square or make x equal to 2, what is 0.5? That's 0.5 times 0.5, which is smaller than 0.5, right? It's 0.25. And if you cube it, it gets even smaller, and smaller, and smaller, and smaller. And then if you make it negative, right? So we said we're getting smaller and smaller and smaller. And then if we make it negative, right? Let's think about 0.5 and then negative 10, right? Well, then isn't that 1 divided by 0.5 to the 10 to the bottom? When we said 0.5 to whatever power makes a smaller number over and over, right? And if you're dividing by a smaller number, and a smaller number, and a smaller number, if you're dividing by smaller numbers, you are getting bigger. So if, oh, I actually lied about the negative. If the negative is out front, I would flip down. I'm crazy. Right, because that says take all your y's to make it negative. But if it's between 0 and 1, it's facing the other way. This should be 4 to the x. And I'm going to go on Desmos for this. Oh. There's one of them. The other one we had was 4 to the x plus 2 on the outside. What do we think that's going to do to it?
Add 2.
Yes, what does that do to the graph?
Makes it slope higher, doesn't it?
Hey, just scoot it up too. Because what you said is you said, take all your y values that you had for this one and just move them all up too. Yeah. And then we had to the x minus 3, but that's in the exponent. Ugh. What happens when I add minus 3 to this exponent? It'll let me. Hello? Do I have to like... What happens when x equals 3 if I put minus 3 there? What happens when x is 3?
That becomes 0, so then 4, it becomes equal to 1.
And where is it normally equal to 1? When x is just 0, right?
Yeah.
Scoot it over to the right. That's all I did. Scooted it to the right 3 units, basically. Alright, because now when x is 3, 1, 2, 3, you're at the same spot when x was 0 here. Cool. It tells us to do it for these ones too. 1/5 to the x. So, goodbye, goodbye. Okay, b was less than 1, so we said it goes the other way around, right? Well, look how close it gets to 0. And look how fast it shoots up. I told you it's crazy. Look at that. When you zoom out, it almost looks like a right angle. What did the next one want me to do? 6 times that? What do we think that's going to do?
Move it over 6.
Think about this. You have your y values equal this graph. If I times all these values by 6, they're pretty much just going to get bigger. It's going to stretch it a little thinner. Right, if you said take every y value you had in the original one and just multiply it by 6, you're just like increasing it by a factor of 6, right? What was the last one? -2. That, like I said earlier, not only are you going to stretch it a little bit, but the negative is going to flip it upside down. Right, if you say take all your y values, make them negative, flip it all down. Okay. By the way, this is probably one of the most real-world things ever, just because every bank ever relies on, and loan and everything else, relies on exponential growth. Right, whether it's a savings account or a loan you pay. According to Newton's law of cooling, I remember doing this in differential equations, but with the differential equation, not exponential stuff. We're like finding like how long a dead body had been out with Newton's law of cooling. Pretty cool. According to Newton's law of cooling, the difference between the temperature of an object and its surroundings decreases in time exponentially. Suppose a certain cup of coffee is 95 degrees Celsius and it is in a room that is 20 degrees Celsius. The cooling for this particular cup can be modeled by the equation y equals 75 times 0.875 T, or y is the temperature difference, important term there, temperature difference, and T is time in minutes. Find the temperature of the coffee after 15 minutes. Literally all we do, T is time after 15 minutes. It is important that it said T is time in minutes, and we were given minutes. My board, guys, please, one of you get rich and just buy me a new smart board, please.
Look, I have better things.
How much are they?
Too much money.
Too much?
How bad they
Too much that RPS can't fix it?
About $250,000 mahogany table, they can't afford to fix it.
are. Yeah, downtown gets a lot of unnecessary money. I'll be in here for me. Mouth shut.
We're all gonna be
And don't tell anyone I told you to keep your mouth shut, because that sounds threatening. I would never do that to you, student.
I don't know. The answer is
You can just say, just shut up.
Shut up. You guys know that video?
the teacher.
Shut up.
Do you know the no pomegranates?
No pomegranates.
Yep.
I'm sure Mr.
That's classic. Well, everyone's got to know that one.
Quick, someone in your head, what's 0.875 to the 15th power?
Oh, you guys do that.
So that's what 0.75 to the 15th power is, and we times it by 75.
Oh, that's good. 10.12.
Now, important thing in the word problem here. Why is the temperature difference, not the temperature? It doesn't make sense that the cup of coffee would get colder than the room around it. Right?
Correct.
So our actual answer for how cold the coffee is going to be 20 degrees plus, that's not a 1, plus 10.1. That coffee is now only 30 degrees, 0.1 Celsius. Yes.
That's hot.
Yeah, it's about 90.
You add it to the 20. Because it's the difference, it's the temperature difference between what the ambient surroundings are.
You really want the coffee to be 90 degrees?
Yeah, because that almost only open on hot coffee. I don't really like coffee.
Yeah.
I don't really like coffee. That's
Really?
my big thing.
I couldn't care less about the temperature of the coffee.
It's not the temperature that bothers me, it's the taste.
Yeah, but like I said, when I did it in differential equations with the much more complicated equation, we were finding like how long the dead body had been out. But like a body dies, it stops producing heat. You can find out how long the body's been dead compared to how cold it is or what the temperature is outside. I'm sure there's a lot of other uses besides dead bodies, but yeah.
No, I think the bodies are the only.
Yeah, no, I'm pretty sure they were like, we're gonna make this specifically so that we can know when dead bodies.
Yep.
In a situation like cooling, when a quantity loses value exponentially over time, or like my happiness, the value exhibits what is called exponential decay.
You okay?
No. I'll be okay in 12 days.
Yeah, we all will.
Okay.
We're all gonna be dead.
Many real-world examples involve quantities that increase exponentially over time. For example, the balance in a savings account,
Listening.
all exponential stuff, or the population of people or animals in a region. This is called exponential growth when it goes up. Importance. Importance. For those note takers, I'll just give you time to write that down or let you abbreviate it. So this is exponential growth or decay, where n is your like final amount that you end with, which is usually the goal of what you're looking for, right? If you want, you usually want to know what you end with. And when we have like the sub-zero here, my physics people can probably tell me, what do you usually call that? Not. Yeah. N not. And then 1 plus r, where r is the rate of growth or decay, to the t. Oh, that thing's almost more obnoxious than me. Okay, this makes sense. Let's say our rate of growth was, I don't know, 50%. Something crazy. And let's say we had the number 10, and then we wanted to increase 10 by 50%. What would we multiply it by?
0.05. No. Wait, yeah, 0.5, that's what I meant.
Did you say it? What did you say? Did you say it? What? No! If we want to increase it, what times do we have it? Oh, we want to increase it. 1.5. Right? Because we want the whole 10 and then 50% more. And that's exactly what this does, right? If we did 1 plus 0.5, then we get the 1.5. And when you take it to the t, you're just timing it by 1.5, and then timing it by 1.5, then by 1.5, and then by 1.5. Right? Every single time you times it by 1.5, you increase it by 50%. What?
Kyle, whose room is next to you?
First one is fine. Oh. And if it's like, if you want like, if it's decreasing by like, I don't know, 20%, right? Then you would times it by 0.8, right, to decrease it by 20%. That makes sense? Right? Because then you only have 80% of what's there, or you decreased it by 20%. And so here it would be like a minus 0.2. Right? So it makes sense. It's there. In recent years, beekeepers have experienced a serious decline in the honeybee population. That's sad and also really bad for us. In the United States, one of the causes for the decline is the arrival of, I don't know, Varroa? Varroa? Sure. Varroa mites. Experts estimate that as much as 90% of the wild bee colonies have been wiped out. The graph shows typical honeybee and Varroa populations over several months. A graph of, I'm just going to say the mites, of the mites population growth from April to September resembles an exponential curve. Right? And this is what I mean by like math model stuff. Right? Like this, hello board, this looks like an exponential hello curve right there, right? And then it kind of dips off here so it doesn't look like it anymore. But from here to here it does, so you can model it like that. Suppose that a researcher estimates that the initial population of Varroa in a colony is 500. They're increasing at a rate of 14% per week. What is the expected population in 22 weeks? Well, it's a good thing we have y, or we shouldn't say y. It was in our other equation. It was n, right? The expected, what we want to end with, is right. What we want equals our initial. That's usually what not tends to be, is whatever initial thing is, which is 500. There's initially 500 of them. 1 plus, it's increasing, so plus at a rate of 14% per week. And we want it for 22 weeks. So really we just have to do 500 times 1.14 to the 22. 500 times 1.14 to the 8,931. That's how many mites they expect after 22 weeks out of 500. Exponential growth shows up a lot in real life and in nature because it grows proportionally.